In this module, I'll cover what we call second-order transient circuits, and these are circuits that contain two storage elements that cannot be combined. So these two storage elements could be a capacitor and an inductor. They're not necessarily directly connected, they're somewhere in the circuit. And we can also have maybe two inductors, so two storage elements. They don't have to be different, like they don't have to be a capacitor and inductor. However, if you have two inductors or maybe two capacitors as well, you shouldn't be able to combine them in series parallel. So they have to be completely separate and different. And if that's the case, you'll end up with a circuit that will result in a second-order differential equations, and that's why we call it second-order transient circuits. So I'll start off in this introduction by covering two of the most basic circuits, second-order circuits, and these are, we call them RLC circuits because they contain a resistor, an inductor, and a capacitor, and in two formation. The first one is in parallel, and the second one is in series. So this one here is called a parallel RLC circuit. This one here is called a series RLC circuits for obvious reason. These are all connected in parallel. These are all connected in series in here. I'll start off with the parallel RLC in here. So in this parallel RLC, what I have is a source, a resistor, an inductor, and a capacitor connected in parallel. So of course, they all share the same V of t, which is a function of time. So in this example, I'm showing you that I of s is actually a function of time, or I could have just simply said like, well, it is DC and I have a switch that closes and open with time. But I'm just going to keep it that way just so that we can derive a differential equation that contains some sort of a function of time in here. All right, so let me just write the equation that describes this particular circuit, and I'll straightforward tell you, let's write a nodal equation. Here's my reference, and that's a V of t, and I'll just write a nodal equation. And that nodal equation will tell me, well, you have negative Is of t, because I'm assuming all the currents are leaving that particular node, and then divided V of t divided by R, plus I will just keep it for now as IL of t, which is the current flowing through the inductor. This is this one here. This is actually just the initial current flowing through it at t0. It doesn't have to be at t0, okay? It can be, for example, t. Let me just keep it at t for now. Plus, we can also say, well, IC of t as well, which is the current flowing through the capacitor. But we should know that simply IC of t is just C dV of t divided by dt. And since I'm actually writing something in terms of the V of t, I'll just basically use the equivalent in here. And of course, based on passive sign convention, I have this is a positive, this is negative, and the current going to the positive, so positive is okay. All right, so we do that here. I'll just replace that with its equivalent, which is C dV of t divided by d of t equals 0. So this is the equation that describes this parallel RLC, and if you take a closer look at it, you will see that we have, well, in addition to the Is of t, which is something that is fixed, we can't control, or we're not interested in because it's a source. What we're interested in is either V of t, or maybe the more interesting part is actually the current flowing through this inductor. So V of t is because it's shared between all of them, and the IL of t because if you think about it and you wait for a very long time, what you will end up with is the following. This will act as an open circuit. If this is basically a DC source, this will open as an open circuit. This will open as a short. So if this is a short, that means the resistor doesn't exist. So the I of t here basically will be the dominant one. Basically, the Is of t will actually just flow through that inductor if the Is of t happen to be DC. So what I will do right now is I'll rewrite this equation in here, either in terms of V of t or in terms of IL of t, either one of them. So I'll start off by saying, let's target the V of t. Basically, let's rewrite the L of t as in terms of V of t. And you should know by reviewing inductors that simply the current flowing through the inductor is just simply 1 divided by L from t0 all the way to t. And that here should be V of x, d of x, plus the initial current flowing through the inductor. And that basically is here. This is IL of t at t0. So I'll just basically take this equation in here and just replace it here. That's IL of t. And what I'll end up with is the following. I'll also, at the same time, move the Is of t to the other side. So I'll end up with the following. 1 divided by r V of t plus 1 divided by L. And that's the integral from t0 to t. That's V of x, d of x, and that's plus I of L. That's the initial current flowing through that inductor, plus C dV of t divided by d of t, and that should be equal Is of t because I moved it to the other side. And now what I want to do is I want to get rid of this integral. So the way I'm going to do it is I'm going to just take the derivative of both sides. So what I will end up with is 1 divided by r dv of t divided by d of t plus 1 divided by L, and that's simply v of t. And of course, well, this has to be 0 because initial current flowing through it is just a number. It's basically 0. And then, of course, this will be c, the second derivative of v of t divided by d of t squared. And that's basically here is of t. Actually, this is the derivative of that. And of course, if that is of t happen to be dc, you can just replace it with a 0 because the derivative or the derivative of a DC source or a number or a constant is just simply 0. So now I'll rearrange the terms so that dv of t squared, this is basically the one with the highest power, so that d of t here divided by d of t, and what I'll do is I'll divide everything by c so that I can get rid of this here. What I'll end up with is 1 rc dv of t divided by d of t plus 1, I believe, lc, and that will be v of t, and that should be 1 divided by c, and you just move these here so that you don't get confused with them, and that here is the dis of t divided by d of t. And that's basically the differential equation that describes this particular circuit. And if you think about it, it's a second order differential equation because it contains v of t, dv of t, and the second derivative of df of t. Okay, and if I, instead of v, I decided, you know what, let's just do that as x. So let me just rename v as x. So I'll end up with d squared x of t divided by d of t squared. And also, if I just rename these constant or these factors as maybe a1, basically let me call this one here is a1 and this one here is a2. Okay, and what I'll end up with is this one here will be dx of t divided by d of t plus a2, that's simply x of t, and then here the whole thing we can just say, well, we usually call it the forcing function of f of t. Again, if that di of s that happened to be dc, the whole thing will be 0 and I will have to replace it with a 0. But I'll just keep it this way because it's more generic. And now what we have is we have a second order differential equation that describes the circuit. And again, what we did target in here is the following. We said, let's find the value of v of t, and that's what we ended up with. We ended up with the second order differential equation. I could have done the same type of things in here, but let me just rewrite that here. So this is the equation that described it. And instead of basically writing it in terms of v of t, what I could have said, you know what? IL of t is a little bit more interesting because that's the current flowing through the inductor, okay, and that I of f of s, like especially if I of s of t is happen to be a DC, that will be the current that is flowing through it. So let me just do the following. I will actually write every v in terms of I of t, okay? And the way we do it is, well, we know the inductor voltage. Okay, I'm just going to write it in here. So the inductor voltage, which is also v of t because it's the same voltage across all of them, is just simply L di L of t divided by d of t. So what I can do, of course, now is I can go, wherever there's a v of t, I can replace it. Now what I have in here is dv of t. So what I also need is actually to take the derivative of this equation. And what I'll end up with is L di L of t divided by d of t. That's actually second here. So what I'll do is I'll take this v of t in here, just substitute it in here, and this dv of t and substitute it in here, and what I'll end up with is the following. So I'll move the I of s to the other side, so I'll move this here to the other side, okay, and what I'll end up with is the following. L divided by r, and that here is simply dIL of t divided by d of t plus IL of t. I'm not going to change it because this is what I'm interested in. And this one here is L C d I square L of t divided by d of t equals I s of t. And I'll rearrange the terms. So basically this is a differential equation that contains IL of t, the first derivative of IL of t, and the second derivative of IL of t. I'll just rearrange them so that the constant in front of the second order is just 1, so I'll just divide everything by L of c, and what I'll end up with is di L of t divided by d of t, plus that will be, I believe if I'm dividing everything by that will be 1 RC, and that's dIL of t divided by d of t, plus 1 divided by LC, and that's IL of t equals 1 divided by LC IS of t. Again, a little bit of change of variable. Let's call this one here is A1, this one here is A2. And you can think about it, we renamed this as A1 and renamed this as A2. They're the same exact thing in here. Okay, and this one here, I'm just going to call it just a different forcing function. So I can just basically rewrite it as the second derivative of x of t plus A1, the first derivative of x of t, plus the second A2 x of t plus a forcing function f of t. So if you take a look at these two green ones in here, this describes the circuit and it's a second order differential equation, and this describes the circuit and it's a second order differential equation. Of course, f of t here is not the same as f of t, but the point is basically whatever you describe it or whatever you're targeting in this circuit, it will be described by a second order differential equation. We can perform the same type of analysis for series RLC circuits, but for the sake of time, what I will do is I'll show you how you get started and I'll give you the final answers without going through the detailed solution. So what we can do in here, for example, just write KVL equation in this particular loop, and what we'll end up with is negative Vs of t plus, well, they share the same current, and that current is IT times R, that's the voltage across that here. And then what we can do is we can say Vc of t. This is not necessarily T0, it's actually t in here. Okay, and then plus, well, what we care about is VL of t equals 0. Hopefully, you do remember that your VL of t is just simply L di of t divided by d of t. So we can substitute that here, Vs of t plus IT of R plus Vc of t plus that here is L di of t divided by d of t equals 0. Or you might tell me, well, you know what, I know that Vc of t is just simply 1 divided by c, and then that's from t0 to t, that's I of x, d of x, plus I think Vc of t0, which is the initial here. So what you can do is now I have a equation in here that contains I of t, the first derivative of I of t. So what you can do is you can just substitute Vc of t in here and you write it in terms of the i's. Then you take the first derivative and you'll end up with an equation that actually can be described with the following. After changing of variables and everything, oh well, before changes of variable, let me just show you that. You'll end up with an equation that basically is di squared of t divided by dt of square plus 1 divided by lr divided by r, basically di of t, divided by d of t plus 1 lc I of t equals 1 divided by l, and that is the v of s of t divided by d of t. And of course, again, if this v of s happened to be dc, that will be just 0. And if you do a little bit of a change of variable, we'll end up with the same equation that we've seen in the parallel case, which is the second derivative of x of t plus a1, the first derivative of x of t, okay, plus a2 x of t plus some sort of a forcing function. That's what we have. Of course, you could have also told me, you know what, instead of just rewriting that Vc of t in terms of the current, what I could have done is I could have taken this V of L here, okay, and that's basically in here. I kept it in terms of V of L, and I could have just rewritten everything so that we can get everything in terms of Vc of t. And what you'll end up with is the following. You'll end up with the following equation, which is the second derivative of Vc of t plus d divided by dt squared plus 1 divided by L divided by R plus d Vc of t, d of t here plus 1 divided by LC Vc of t plus, or not plus, that will be equal to 1 divided by LC Vs of t. If you do compare, you will see that this one here is A1, it's the same A1 in here. This one here is A2, it's the same A2 in here. And this one here, while it's not the same forcing function as the one, but it's a forcing function. And you end up with the same second order differential equation that describes series RLC circuits. In the same way that we described, actually it's the same type of equation or the same form of the equation that described the parallel RLC circuits. It's exactly the same. Maybe the A1 and the A2 are not the same, but if you just ignored that fact that this is 1 divided by RC instead of 1 divided by L divided by R, it's of the same form. So as it turns out, if we can figure out the solution for this second order differential equation, we should be able to figure out the solution for that particular circuit. And the solution, before I get into the details of how we solve it, I'll cover it in more details. What I want you to understand is the following. The solution comes in 3 different cases or shapes. So it's either an overdamped solution, an underdamped solution, or a critically damped solution. For now, what I want you to think about is the following. You have some sort of initial value in here, and in all cases, I basically approach almost 0 at the beginning, and the final value for x of t, which could have been a voltage or current, happened to be 100. This is 100, that's the final value, and this is 100. So in an overdamped, what you will see is a sluggish approach to that 100 that we want. So it took it about 3, let's say whatever that 3 could be, second, millisecond, or whatever it is, to get to the 100. In an underdamped response, what you do is we will get to that 100 very quickly. It's less than 0.05 of that time. But what happened is we had some jittering or oscillation around that final value. And of course, we reach a very high value, in this particular case, 140. So if we're dealing with electronic equipment, that 140 amps might actually blow up some of these electronic equipment. So it might not be needed. So you have to evaluate whether you want it to reach the 100 slowly or whether you want it to reach it quickly, but maybe your electronic equipment should be able to handle this oscillation. The last form in here, which is critically damped, it's actually in between. So it's not as slow as overdamp, but it's not as quick as overdamp. But the problem with it is it's very difficult to approach it. You will have to have exact values of R, L, and C, or whatever parts that you're using in that circuit.